In 2011, scientists using the South Pole Telescope in Antarctica observed more than 24 distant galaxy clusters, 12 of which had never been seen before. Among them was the Phoenix Cluster, a group of about 1,000 galaxies bathing in blistering radiation, with its biggest and brightest galaxy unlike anything we'd seen before. In the decade that followed, the Phoenix Cluster enjoyed a meteoric rise to become one of the most extensively studied galaxy clusters in the universe, shattering a number of cosmic records for X-ray emittance, gas fractions, and star formation. But lately, it has taken on a significance of another kind, because, at the heart of the Phoenix Cluster's unique central galaxy, lies perhaps the largest black hole in the universe, one with a mass claimed to exceed entire galaxies and dwarf the inner solar system with its event horizon. The question is, why do people think that this black hole is the largest, and more to the point, who are those people, and what information did they use to draw their conclusion? Furthermore, just how large can the biggest black holes really grow? And if this one is not the largest, which is? These are the questions we will be answering as we search for the universe's biggest black holes. Black holes are volumes of mass that are so densely compressed that their gravitational influence deforms the space surrounding them. Inside a region of warped spacetime, the force of attraction becomes so great that the escape velocity needed to leave exceeds the speed of light, and thus not even massless photons can break free to meet the eyes of an observer. Instead, they fall straight towards the center, resulting in a lightless sphere of unrendered space around the concentration, known as an event horizon. Though the concept might sound ominous, the science is anything but. Any time we compress enough mass into a sufficiently minuscule volume of space, an event horizon of sapped light will form around it. And in a universe dominated by gravity, there are a number of ways to achieve a gravitational collapse. Mini-quasar binary systems like GRO 1655-40 provide us with compelling evidence that black holes form from the leftover cores of collapsing stars. When a giant star goes supernova, only its outer layers ignite, leaving the inert core exposed, which collapses in on itself in the absence of an energy source. If this collapsing core weighs more than a few times the mass of our Sun, then it will continue to compact and compress its volume until an event horizon forms around it. This gives us a stellar black hole, with a mass ranging from a few times that of our Sun to a few dozen. By far the smallest and most common kind, the Milky Way alone may be littered with the corpses of millions of its bygone stars. While the majority of these remain invisible and undetectable in the vastness of space, some stellar black holes light up as they feed on their surrounding gas. Black holes grow via accretion. The shredded matter closest to the event horizon, under the greatest tidal influence, collects into a thin, rotating disk along the black hole's axis. On the inside of this disk, a small fraction of excited particles will eventually experience enough drag force to guide them below the event horizon, where they plunge towards the center and grow the black hole's mass. But the majority of the disk's matter will remain outside, instead orbiting the horizon at obscenely high velocities and temperatures. Thus, the process of accretion is a fairly slow burner for a stellar black hole, allowing it to accrue a few dozen extra solar masses of material over many millions of years. Eventually, it may reach 100 solar masses, at which point it would be classed as an intermediate mass black hole. Considerably rarer than their stellar counterparts, intermediate mass black holes start at a century of solar masses, for the largest collapsed stars, but they can grow to tens of thousands, for those beasts we see lying at the hearts of star clusters and disrupted proto-galaxies. But at this insane weight, black holes of an intermediate mass are surely too large to have been built up by accretion alone. There must have been another mechanism supplementing their runaway growth. And indeed, we do see evidence of such a mechanism, realized when black holes collide. When two of these monsters find each other in space, they soon begin spiraling in on one another as their orbits decay, ultimately destined to join their event horizons and merge their masses. This facilitates the snowballing-like growth of gargantuan black holes on a variety of scales in binary systems, during chance encounters, and even during the collision of galaxies. Lying at the hearts of most galaxies, we find the largest type of black hole, a supermassive black hole, with a mass greater than at least 100,000 suns. Almost every large galaxy houses one of these beasts in its nucleus, and for particularly large, mature galaxies like the Milky Way, Andromeda, and M87, they can grow to millions of times the Sun's mass, large enough to swallow stars in a single gulp. These black hole nuclei are thought to have played a vital role in establishing the shape of their host galaxies, particularly in the core region, with the highest concentrations of stars. And thus, where we find massive, oversized galactic cores, we can expect to find similarly massive monster black holes. As such, it is easy to see why the nucleus of the IC 1101 galaxy, IC 1101, has long been viewed as a principal candidate for the largest black hole in space. IC 1101 was once thought to be the largest galaxy, with a diameter of around 6 million light-years, according to early, overly generous estimates. This figure has been reined in by more than half in recent years, but in any case, the galaxy still boasts one of the largest nuclei we've ever seen, extending about 13,500 light-years. And this massive galactic bulge weighs in favor of a similarly massive black hole at the center of it all, believed to have a mass in the region of 40 billion suns, corresponding to an event horizon radius exceeding the orbit of Neptune dozens of times over. For a black hole this insanely large, supermassive, doesn't do it the proper justice, and so, for those monsters whose mass exceeds 10 billion solar masses, we refer to them as ultramassive black holes, or stupendously large black holes, aka, slabs, in special cases. And like the black hole at the heart of IC 1101, many of the largest slabs we've pinpointed tend to lie around this 40 billion solar mass mark. A handful with even greater masses have been proposed, but none with conclusive evidence derived from direct observations. In fact, scientists aren't even sure whether black holes larger than about 50 billion solar masses can exist, due to the physics playing out in the accretion disks that grow them. Above around 50 or 60 billion solar masses, the associated disk feeding such a black hole would become so enormous that its matter would likely condense into stars, long before it reached the event horizon. The resulting radiation emitted by these stars would then severely hamper the conditions in the rest of the accretion disk for feeding, curtailing ultramassive black hole growth around this threshold. Thus, we weren't expecting to find a black hole larger than about 60 billion solar masses, that was, until we found TON 618. The 618th entry in the Tonnant-Sintla catalog refers a radioloud quasar, the brightest and most energetic type of galaxy, which is drowned out by its dazzling central engine, an active black hole. This particular quasar harbors an ultramassive black hole, one so vast and powerful that it challenges our understanding of black hole growth and limits. The current estimated mass of the black hole at the center of TON 618 is a staggering 66 billion solar masses, making it the largest black hole known to science and a true outlier in the cosmic landscape. This finding forces astronomers to rethink the mechanisms that could allow such a black hole to grow so large, and whether there might be even larger black holes lurking in the universe, waiting to be discovered. Own blinding emissions, stirred up by its black hole's accretion disk. This enduring light source shines from a depth of more than 10 billion light-years, yet it is so luminous that it was mistaken for a local blue star in the Milky Way galaxy for more than a decade following its discovery. However, in 1970, radio surveys revealed the source to be a quasar powered by a colossal, accreting black hole. When scientists attempted to reverse engineer the properties of this black hole from its spectral data, they discovered that matter must be crossing its horizon at more than 7,000 kilometers per second, in order to generate its profile of emissions. Such ungodly speeds and their associated temperatures could only have been the product of the gravitational influence exerted by a record-breaking black hole, with an unfathomable mass of 66 billion times that of our Sun. At such an extraordinary weight, the event horizon of this beast would stretch for little under 400 billion kilometers, with a radius more than 40 times the distance between Neptune and the Sun. Unfortunately, however, this estimate has been rolled back somewhat in recent years, now more aligned with the mass of IC 1101's black hole of around 40 billion solar masses. But either way, it is TON 618 that has enjoyed the most success in capturing the hearts and minds of amateur astronomers. Appearing in size comparison videos, news articles, and on discussion forums, this black hole has become something of a people's champion, a designation which instantly springs to mind when contemplating the largest black holes in the universe. And yet lately, there have been murmurs of a new champion, with a mass that smashes TON 618's previous record, and its name is now also starting to crop up on sites like YouTube, Reddit, and Wikipedia, claimed to be the new largest black hole in space, the monster lying at the heart of the Phoenix cluster of galaxies. The Phoenix cluster is some way closer to home than TON 618, about half the look-back distance at 5.8 billion light-years. As we mentioned, this 1,000-member galaxy grouping was discovered in 2011, and in the years since has rapidly risen to become one of the most intensively studied galaxy clusters. The Phoenix cluster is unique in a number of ways. It was the most X-ray luminous cluster that had been identified at the time, with some of the highest fractions of gas and rates of star formation, particularly in its dominant central galaxy. Ordinarily, brightest cluster galaxies, which lie at the hearts of certain types of clusters, are not very hospitable environments for star formation, igniting new stars at a rate even slower than the dormant Milky Way. While they do house large quantities of intra-cluster gas, this matter rarely cools to a temperature at which it can break out in prolific starbirth. Rather, BCGs tend to be hives of hot plasma, with an old stellar population flooded by ionizing radiation, owing to ejections from an enormous, centralized black hole. As the gravitational focal point of its galaxy cluster, a BCG is usually grown via the accumulation of progenitor galaxies, concentrating at the heart of the cluster along with their black holes. This leads to a proliferation of seismic black hole merger events, eventually yielding a tremendously oversized beast tens of billions of times the mass of the Sun, surrounded by multitudes of gas upon which it can feed. And as matter crosses its event horizon, enormous amounts of gravitational potential energy are released, manifesting in the form of a series of high-energy outflows. These outflows, erupting from a pair of astrophysical jets, cascade through their surrounding interstellar gas for thousands of light-years, heating it up in the process. This keeps the majority of a BCG's interstellar medium too hot and energized to condense, strongly suppressing the formation of new stars, ultimately rendering the galaxy's morphology as some variant of an elliptical galaxy, with flatlining rates of starbirth. But rather unusually, that's not what we see in the Phoenix cluster's BCG, Phoenix A. In fact, this galaxy is a stellar factory, grinding out stars at a rate hundreds of times higher than the Milky Way. Phoenix A is classified as Type II Seyfert galaxy, the second most energetic type of active galactic nucleus, where the core is overflowing with excess radiation and light, but not enough to drown out the rest of the host galaxy, like within a quasar. Phoenix A derives most of its centralized luminosity from a packed population of freshly fused stars, atop thick blankets of radiant star-forming gas. The first evidence of abnormally high star formation rates in this galaxy was detected in 2012, and soon after, NASA's Chandra telescope saw trillions of solar masses worth of rapidly cooling gas concentrated around the BCG, greater than the mass of all other 1,000 cluster constituents combined. This gas expels heat as it glows in X-radiation wavelengths, allowing it to cool to a temperature better suited to the production of stars. As mentioned, the Phoenix cluster was the most X-ray luminous that had ever been identified, with the highest rate of cooling gas ever seen in a BCG, more than 3,000 solar masses a year. And this cooling is what enables the unusually high star formation rates seen in Phoenix A, as it grinds out over 600 suns worth of new stars per year compared to the measly single solar mass churned out by the Milky Way. And when the Hubble telescope focused its eyes on Phoenix A, it saw these stars arranged into an enormous series of great filaments, measuring 330,000 light-years by 160,000, both longer than the entire Milky Way galaxy, and the largest such filaments ever discovered. Such unusual features point to a lack of black hole activity in the galaxy's recent past. If it were any other way, we wouldn't see such big breakouts of star formation within the swathes of cooling gas. However, if we observe Phoenix A in another wavelength, X-ray cavities and eruptions, we do see signs of active galactic outbursts, imprinted upon the cluster's emissions profile. Above and below the stellar filaments, we see a pair of cavities carved in the structure's X-ray footprint, echoing areas which have been emptied of their cooling gas, most likely due to an eruption from its black hole feeding. The larger pair of cavities, in particular, point to an extremely powerful outburst about 100 million years ago, which sent an enormous shockwave cascading through the galactic medium, hollowing out the region of star birth by dispelling cooling gas. The question is, what could have caused this black hole to undergo such a powerful outburst? To answer this, we need to probe the apparent double personality of the galactic nucleus, which derives around half of its energy from a pair of astrophysical jets, like a radio galaxy, while the other half is powered by friction in the accretion disk, like a quasar. Scientists believe this 50-50 split is likely to be the result of Phoenix A's nucleus flipping from radio galaxy mode to quasar mode. 100 million years before we are observing this galaxy, its radio jets would have ignited into a hyperluminous bout of quasar activity, producing the shockwave which permeated its surroundings, before settling back into radio mode for a second, less significant eruption tens of millions of years later, echoed by the inner cavities. And ever since, the black hole has been lying dormant, unable to reheat its surrounding gas, allowing it to cool, and enabling this brief, fleeting window of star formation we see to commence. So, where does the proposed size of Phoenix A* come into all of this? Why, almost a decade since these revelations, has it only now been assigned as the new largest black hole? Well, it is the size and scale of these larger cavities that point to an eruption amongst the largest we've ever detected, the likes of which could only have been produced by a black hole with the most extreme properties. With this in mind, in 2015, scientists at the Max Planck Institute for Radio Astronomy developed a new framework for locating the biggest black holes in the universe by searching at the hearts of galaxy clusters. In the paper, the authors highlight the black hole at the heart of the Phoenix cluster as a candidate slab, which based on their model, may warrant a mass in the order of 100 billion solar masses, more than double the theoretical limit. And it is this mass prediction that has shaken up conversation surrounding the largest black hole in recent months. At 100 billion solar masses, Phoenix A* would be more than 24,000 times the mass of our galaxy's central black hole, SAG. A*, and about 7% of the mass of the entire Milky Way galaxy, not to mention more than double the mass of the Triangulum galaxy. Such a description-defying weight translates to an event horizon stretching for more than 500 billion kilometers, with a diameter, 3,900 Australian dollars, 100 times greater than the median distance between Pluto and the Sun, 40 Australian dollars. Such a beast of a black hole would present a serious challenge to what we thought was possible. However, one has to examine the context of this estimate before getting carried away, as it is not based on any direct measurement of Phoenix A's dynamics. In fact, this paper gave the same ballpark estimate of 100 billion solar masses to no less than 3 central cluster black holes, not just to Phoenix A*, but to IC 1101*, and the black hole at the heart of another BCG, Holmberg 15A. But we know that IC 1101's black hole is probably not quite as large as 100 billion solar masses, more likely to be in the range of 40 billion, perhaps. And similarly, our most intricate and precise measurements to date of the Holmberg 15A galactic nucleus also suggest a black hole of around 40 billion solar masses, not 100. With this in mind, it would not be unreasonable to cast doubt over the claim of Phoenix A's black hole being so large. In fact, the apparent inability of the black hole to prevent star birth en masse with its ejections, has some proposing that Phoenix A* may be undersized compared to its cluster, and thus unable to sufficiently reheat its gas. In reality, the true mass of the Phoenix A central black hole is likely to be much closer to the 40 billion solar mass mark predicted for our other stupendously large black holes. But as enthusiasts, we are always intrigued by the thought of a new record-breaking discovery, and a new largest entity in space. Unfortunately, however, the notion that Phoenix A* exceeds 100 billion solar masses, which has been so widely touted as a new largest black hole in recent months, is not based on any new research or discoveries. It is in fact an outdated, indirectly derived estimate, which has been plucked from an older paper for the purpose of inflating a new largest black hole. And ever since, this figure has been swept up by the internet, gaining virality in a manner similar to TON 618, appearing in black hole comparison videos, news articles, and cropping up in online discussions, often citing the 100 billion solar mass figure given by this paper. But the truth is that the Phoenix A central black hole is probably not the largest we've ever found, and is almost certainly less than 100 billion suns. The problem is that we don't yet have a reliable direct means to conclusively pin down its true mass. Sadly, the more distant active galactic nuclei at higher redshifts are notoriously difficult to study, and we are limited to indirect estimates for the time being. But new, more reliable and innovative techniques are being developed and applied to other galactic cores slightly closer to home. Just this year were scientists able to pin down the mass of another ultramassive black hole, some 2.5 billion light-years distant. Early in 2023, scientists used measurements of gravitational lensing to constrain a precise estimate for the mass of the monster at the heart of the Abell 1201 galaxy cluster BCG, as being about 32 billion solar masses. Though slightly less massive than some of the aforementioned, this figure comes with a much lower margin of error, and will likely pave the way for the technique to be expanded to more distant active galactic nuclei. There's also that other ultramassive black hole we spoke about earlier, Holmberg 15A, within a giant elliptical galaxy 700 million light-years from Earth. The black hole at the heart of this galaxy is another whose size has been historically beefed up by overly optimistic predictions, with studies in the early 2000s proposing its mass to exceed 300 billion suns. But in 2019, this figure was substantially reined in using our most detailed observations of the galaxy's nucleus to date, to a more modest 40 billion solar mass figure, in line with the aforementioned. Something that may be a fraction larger is the unnamed stupendously large black hole designated for C+74.13, an active galactic nucleus at the heart of a BCG around 2.6 billion light-years from Earth, in the constellation Camelopardalis. In 2005, this galaxy was found to have experienced an enormous outburst, which churned out the equivalent of hundreds of millions of gamma-ray bursts, over 100 million years, also giving rise to a pair of X-ray cavities, both measuring 600,000 light-years in diameter. Such an extreme, far-reaching eruption resolves to an ultramassive black hole growing at an alarming rate as it devours a progenitor galaxy, at least 15 billion solar masses, but perhaps as much as 51 billion, where it teeters precariously on the limit of our theoretical model. However, with so many unpredictable, unseen variable factors, it is difficult to tie down the ejecta of eruptions to precise estimates of a black hole's mass. There's a lot of ambiguity, and it will take many more years of observations before we are able to definitively establish the masses of the largest galactic nuclei. In the meantime, however, we are forced to conclude that no known supermassive or ultramassive black hole that we found yet defies our theoretical limit of 50 or 60 billion solar masses, and that includes Phoenix A star. As it stands, TON 618 is still our best shot for the largest black hole in the known universe, not least because of its extraordinary depth. Explaining how a black hole could grow so massive is one thing, but so quickly, is another question entirely. It truly bends the mind. But what is even crazier to consider is how large that black hole must have grown today, in the 10 billion years since its light we are observing was emitted. It must have cannibalized billions of extra solar masses in that time, which would render it by far the largest known black hole to humanity. For now, though, we can never know. If you liked what you just saw, then please consider subscribing to help the channel. But otherwise, thanks for watching, and I'll see you in the next episode.